Okay. Welcome back to our computer vision class. Hopefully that you enjoyed your break because we have rich and intensive rest of the semester. So hopefully that you finish all your breaks because after that there will be no breaks. So far we learned about, if we go back to our steps that we said we will follow, we said that our goal now is to find features in our environment. Then those features, we will call them key points. Those key points will be points of interest that we have in the environment where we are expecting to find useful information about the environment around them. Those useful information around them, we will call them descriptors or feature vectors. Okay, so the feature vectors are the area around or surrounding every key points or points of interest we found in the environment. After we extract the key points and the features, we will finish up by using the matches. We will finish up by doing matches between these matches between those descriptors around the points of interest to found the point of match between the frames for several purposes, for stereo vision, for panorama integration, for any application. But the main concept lies with those three steps. First, points of interest generation or searching, then feature extracting, then the matching process. Last time, we discussed one type of those points of interest, which was the corners. We said that there are two types of points of interest. The first type is the corner. The second type is
the edges, the lines.
blobs.
Oh, blobs.
Okay. The lines is useful for features, yes, to understand the environment, but the main key points are corners and blobs. Okay. For the corners, we learn how to extract them using the Harris algorithm. Okay. And we show how we can extract those features for any kind of given image. Now, the question is, if I give you two images, two different images that have been extracted or captured in two different locations, are they matching the location for the points of interest? Meaning, if I start with this image, I found those points of interest. And so on. If I go to the same location in the image, here, will I find the same points of interest? Like we said before, that we are dividing or converting the image into coordination. This is the X coordinate, and this is the Y coordinate. Okay, so here I found corner at point, let's say X 100, Y is 2. If I go here to 102, will I find corner similar to that here?
No.
No. Now, this is a problem. Look to the giraffe or whatever this dog, whatever it is. The same corner found here, I found it here, but in another location in the image. It's the same exact corner, right? About the hole. But here the location is different. Can I make a matching between them while they are in two different locations? The answer is yes, I can. But I need to define something which is called feature invariant. What does this mean? If I change or generate another variation from the same image, will I have the same feature points at the same location, or it will change based on that? If you think about this problem, you will see that I can change the image in two ways. One of them called geometric change or geometric transformation, which include rotation and scaling. The other one called photometric transformation, which will include intensity change. Here in this example, do we have both or we have one of them? Actually, we have both. Because this one captured in highlight, this one is a darker line. So we have intensity change in the image. Second thing, this one has a rotation, but the rotation here is not 2D, it's 3D rotation. So if you can see, the rotation is completely 3D. The face or the neck is completely twisted. So I can have rotation, I can have scaling, I can have intensity changing. The rotation and scaling doesn't have to be in 1D or 2D. No, it can be also on the third dimension. Now, how those transformation can affect my features? To understand this, I have to define two things first. Something called invariance and another thing called equivariance of the meaning. The word invariance means if I have two images and I detected object or feature at some point here, let's say the same coordination that we stated, 102, then if I go to another image, I have to find the same exact feature in the same exact location. If this happens, I will call this feature or this key point an invariant, meaning it has not been affected by anything. So the word invariant means if the image suffers from any transformation, the corner location will be stay in the same place. Let's give an example for that. What's the example of transformation that I apply to this image and it will be invariant? Those are the transformation we discussed. Which one of those, if we apply to this image, it will be invariant? If I change the illumination, the corner will stay in the same place or no? So yes, this way, sorry, the photometric invariant. So if you change the illumination, the corner will stay in the same place. How about if I do rotation or scaling? Scaling has many words to talk about it. Rotation, absolutely no. It will not stay in the same location. And that brings us to the second case. If the feature still exists, but changes the location, in this case, we will call it equivariance. So the invariance means feature exists in the same exact location for the two images. The location will never change. Equivariance means the feature exists, but in another location. Okay? So this one exists here. So yes, it could find it, but in a different location. So this one, for example, is at 30 and 10. But it's the same exact feature. So it didn't skip, it didn't disappear. That's why we can say that this is an equivalent features. Okay? In some books, you will see some people call the equivariant invariant and vice versa. Okay? But officially, they are different. Also, some people may call the equivariant as covariant. Again, those are just naming convention. Now, we want to cover or study the corners that we introduced for the last lecture, according to these rotations, if they are invariant or equivariant or none of them. So we'll start by the shifting, the translation. Assume that we have an image that has a corner. This corner is here. Then I translated this image to another location. So the corner is here. Did the corner disappear? No. So the feature still exists. Does the corner stay in the same location? No. So in this case, this is equivariant against translation. So the translation will be able to find the corner, but in a different location. That's why we call it equivariant. So the conclusion from that corner location is equivariant with respect to the translation. How about the rotation? Again, corner here, corner there. So the corner exists, didn't disappear. But the rotation will change the location. So here, I'm in some location, x1, y1, and here I'm in another location, x2, y2. So we can say that the corners are equivariant with respect to the rotation. How about the intensity change? So let me refresh your memory. What is the meaning of intensity change? Intensity change means I'm trying to generate a new function of x or y, which equal the old one plus some variable or another function of this values. Okay, so it can be by adding constant, maybe by put it to the power gamma, or anything of this change. Remember what we do with the image enhancement in the beginning? So that's how we can change the intensity of the image. Now, assume that we did the intensity change. Will the corners in the given image will exist or will vanish? That depends. So, to simplify the problem, we will see a simple 2D representation of the Harris cooperator. So the Harris coefficient or the Harris value. Remember the Harris value that we calculated from the last lecture, which is a combination between the trace and right. So let's check the value of this over the given image coordination. If you will see, at some specific point, it will have a maximum. So we have a corner. Here we have a maximum. We have a maximum. Based on the sum thresholding, those maximum will survive and will have 3 corners. But based on changing the intensity, this one of them may vanish or another corner may appear. So a corner that didn't exist before may exist, or a corner that existed before can disappear. That means that the corner detection technique is partially invariant with the intensity change. Why we said invariant? Because the corner will exist in the same location, it will not change. So if it exists here, it will be exactly here. The location is fixed. Here is here. Let's go to the example of the beam. If it's here, then it's here. No change. The location is the same. So the corner exists and the location exists in the same. The location equal for both images. That's why it's invariant. But if the corner vanish, then it's not invariant. That's why we are saying it's partially invariant for the intensity change. So this depends on the case of your adjustment. Finally, we have the scaling. Assume that we have image that has corner, and I scale this image up or down. Will the corner still exist in this case? The answer is maybe yes, maybe no. So if you are scaling up as an example, the corner is obvious here. So the algorithm will detect the corner no matter what. But if you zoom a little bit on this curve, there is no corner anymore. It becomes smooth. So there is a corner here, but it's not a real corner. Here, all of them are edges. This is a real corner. Here, it's an edge more than a corner. So we can't guarantee any invariant or equivariant against the scaling for the corner. That's why we can say that it's neither invariant nor equivariant to scaling. So Harris detector can suffer from a big problem when the image scale change. That is a good thing what happened. If my features suffer from the scaling invariant, what does this mean? It means that if I hold my camera right now and capture a picture for this bench, then I approach a little bit and capture another picture, and I try to make matching between them, I will not be able to find match. Because the corner detected here completely different from the corner detected there. Some of them be detected here, not there, and vice versa. Is this a good thing or a bad thing? Can we solve it? We said yes, we can. How? Our goal now to find the technique, to find this small tiny corner that existed here for this bigger version of it. How can I do it? If I give you image, that has two faces. One from this size and another one with this size. And I asked you to detect both of them. with an algorithm that work only on some specific size, what you will do? Logically speaking, I will try to fix the size. So assume that I work on the smaller size and detect its location. Then I will try to generate different scale version from the image. So I will have smaller version, another smaller, and so on. Then I will try to make the detection for the bigger one onto those smaller version until I find it. That's exactly that we can do here. So we will start by detecting the corner on the lower scale, then increase the size of our detector to work on bigger, then increase the size to work on bigger. Let's have an example. So assume that we want to detect the corner here in this area and match it with another corner for another scaled version from this. So we'll do what? We will start at some specific scale, find the value of the coefficient. Then scale up this window and find the coefficient. Scale up the window, find the coefficient. Scale it up more. Scale it up more. Scale it up more. So I will find the coefficient value for several scales. Then I will find which scale give me the maximum coefficient value. So here, for example, the maximum coefficient value captured at 3.89 at this value. So this means the best corner can be seen within this scale. Now, if I give you another version from the same image, then you can do the same exact thing we did here. So I will find the coefficient value on this scale, then more scale, more scale, more scale, and so on. Then I will find the scale that give me the best coefficient value. Now, if I scale this down with this scale value and scale this down with this scale value, will they match or no? The answer is yes. So this is the smaller one, I scale it with this scale value. This bigger one, I scale it down with this scale value. So this exactly matches. Again, instead of looking for one image for one size, no, I will generate for myself different window size for the detection and find the coefficient value at each scale level. Then, if I have another image I want to match with, I will do the same exact thing with it. Then I will find the scale that give me the highest coefficient value, the scale that give me the highest coefficient value, take those coefficient windows, scale them according to this scale, then I can do the match between them. Make sense? Now, what I'm discussing here right now is generating different scale from the window itself. Remember, for the highest corner detection, we have a window size. This window size, we are shifting, right? So if I increase the window size, I can find the corner within a bigger window. But I can do the opposite. And instead of increasing the window size, I can reduce what? The image. So I can generate a Gaussian pyramid. Remember the Gaussian pyramid that we covered before? So instead of generating different window size from the image, no, I will fix the window size and generate image pyramid from the given image. Based on that, I will write the scale against the window. So this is at scale 1, this is at scale 3/4, this is at scale 3/4 times 3/4, which is 9/16, and so on. Okay, so I'm going down with the scale and make the window fix it in all of them. Now I will find the corner value, the coefficient value at which scale achieve the best value, and this will be the scale used for the matching. Okay, so instead of calculating the scale for the window size, I will calculate the scale of the Gaussian pyramid. Is this clear? Okay. Now we solved the problem for the Harris corner detection. Now it becomes equivalent against translation, equivalent against what? What do we say? Rotation, then partially invariant again scaling and illumination. Okay, and regarding the scaling now, we solve it by working on multi-scale from the given image. Okay, so we concluded. So equivariant for translation, equivariant for rotation, partial equivariant, invariant, sorry, for intensity change, and if we work on multi-scale, we can achieve equivariant against the scale. Any problems so far? Okay. So this is regarding the corners. We could find the corners right now. Next part of the game is blobs. How can we find or detect blobs in a given image? This said, let's go back a little bit. Remember, when we thought about detecting the edge, we said that we can detect the edge by having the first derivative. But when we have the first derivative directly, if the data is noisy, the first derivative will be completely noisy. That's why we apply Gaussian filter on this data, then we take the first derivative. And from that, we got the concept of Sobel filters, if you recall. Now, another solution that we introduced by that time was calculating the second derivative of a given image, then find the zero crossing point. And by that time, we call the second derivative for the filtered version of the image as Laplacian of Gaussian. So it's the second derivative of the Gaussian filter applied to the given image. This Laplacian of Gaussian is our key point to understand the blobs. How? This said, let's apply or think about the Laplacian of Gaussian from the 2D perspective. How it will look like. For the 1D, that's how it will look like. Coming here to 0. Here has 2 beats up over the 0. Then in the middle, it has a negative value going big down. If we talk about the 2D version from this, think about rotating this around this axis, like a donut. It will generate this version. So from the sides here, flat, almost 0. Here, it's curved a little bit, up. And in the middle, it's extremely sharp. If you plot the 2D view or the image view for this value, that's how it will look like. Here, deep dark. Here, almost gray, which is 0 value. And here is white because here it's positive a little bit. Now, this Laplacian of Gaussian filter will be our plot detector. How? We will use this on a given image. And we will see what exactly it can find. If we apply it to a given image, that's what we can get. So this is the Laplacian of Gaussian. If you apply it to a given image, that's exactly what you got. This is the output. If you take a deeper look to this one, you will see that we have all the plops value become minimums or maximums. So if I apply this Laplacian of Gaussian filter to any image, I can detect the plops of the image by finding the maximums and the minimum value within this output. Very straightforward. So which one is easier? This or the corner? Calculating the Laplacian of Gaussian is easier, or calculating the corner? Which one is faster?
Well, looks like that. Looks like that one, because it's less steps.
Here we're only applying one convolutional step, right? Apply this filter to the whole entire image, you will get the plots that you want. It has one small tiny drawback, or two, to be more accurate. First drawback, the plot size detected is 100% function of this sigma value. If the sigma value of this Gaussian filter is small, it will be able to detect small plots. If the sigma value is large, it will be able to detect larger plots. So I will not be able to detect all the plots in the image using this technique. This is the first problem. Second problem, from the calculation perspective, generating the Laplacian of Gaussian for every plot size will be time consuming. Because I just said, one filter will not be able to generate for all plots. I have to generate different versions for every plot size. So generating multi-version of this Laplacian of Gaussian filter will be time consuming. So we need to find some solution to twist this. Before going to the solution, what is the relation between the plot size and the sigma value? They said, if we have a plot size of a radius r, in this case, the value of sigma of this Laplacian of Gaussian filter must equal r over square root of 2. This is the relation between them. So increase R, increase sigma. Reduce R, reduce sigma. When I change sigma, what else change in the filter? Assume that I'm increasing sigma. What else will change in this filter? What does it?
Sorry, that area becomes.
What does this mean? What does this mean?
The radius increases.
Okay, let's take a practical example. So assume these are equal 10 pixels. Okay? In this case, the value of sigma would be what? 10 over square root of 2 equal what? Can someone calculate it? Equal? 6.9.
9.
Okay. Now, what is the size of the filter that should have sigma equal 6.9? Nothing? Okay, tertiary, because we will have it in a minute. So, this way, I have to keep changing the value of sigma for every plot size I need, and based on that, I have to change the filter size. So the filter size, in this case, is not fixed. It's variable. Okay? So this is one of the drawbacks of working on this problem. So if I have some image and I want to detect a plot inside, I will keep working on different scales from the filter. So several values, then find the B value of the Laplacian at which scale, and this will be my plot size based on that. Okay. Now, can we twist this around? They said yes. How? We will play similar games like what we did with the Harris corner, but with the Laplacian now. So if we have specific image, we will have an initial Laplacian Gaussian filter value. We will start with the specific sigma value. Then I will find the maximum and minimum at that scale and put it in a record. So the maximum and minimum at this X and Y coordination, and S is the scale I got this value for. Then I will generate Laplacian of Gaussian value on square rooting the sigma. This means I'm increasing the sigma. Then find also X and Y and S at that. Then cube it. Find the maximum and minimum. Fourth it, maximum and minimum. Fifth it, maximum and minimum. In this case, I will have scaled version of the plots with the maximum and minimum of each value. Based on that, I can find which one of them that have the highest value, and I can detect the correct plot size based on this. Again, instead of changing the scale and calculating the Laplacian Gaussian this way, I will start first by having initial value of the sigma. Then calculate the maximum and minimum on this scale level. Then change the sigma value by having sigma squared. Calculate maximum and minimum on this scale. Q, maximum and minimum on this scale. Fourth, similar. Fifth, similar. So I will have several layers. Each one of them has the maximum and minimum on the scale value. I can pick which one of them has the best value at which scale. Based on that, I can detect the size of my block. Okay? So this can solve the scaling issue or the scaling problem or the resizing issue of the Laplacian of Gauss. So if we have image like this, we can easily calculate several values of sigma for this image, and we find the maximum and minimum and put the record for this location with this maximum and minimum values, then compare with the three of them. Not three, many, multiple of them. In this case, we can find the blobs on all scales, as you can see. Any problem so far? So now we can generate blocks on several scales, and we overcome the problem of having the sigma or generating specific sigma for a specific block size. Come to the second problem, generating the Laplacian of Gaussian itself. To generate this Laplacian of Gaussian value, we need to calculate the Gaussian, then the second derivative of the Gaussian for the x direction, the second derivative of the Gaussian on the y direction, add them together so to produce this one. Is there a better way? They said yes. We can play the same game using another thing called difference of Gaussian. Hold on. This said, if you have Gaussian function with a specific sigma and another Gaussian function with another sigma, if you subtract those from each other, the result of this subtraction will look exactly similar to the Laplacian Gaussian. So I don't need to find the derivative or the second derivative or make any addition. I can easily convert or calculate an approximated version of the Laplacian Gaussian using the difference of Gaussian technique. So the concept of difference of Gaussian means I will make subtraction for two Gaussian functions at different sigma values. This subtraction will produce signal very close to the Laplacian of Gaussian signal. We will call this signal difference of Gaussian. Okay? Now we overcome the problem of the computational issue of the Laplacian of Gaussian. It's just subtraction, subtract this minus this. There is no differential, there is nothing. You don't need to find any derivatives. Okay? Now, we overcome the two problems right now. The derivative and the scaling. Can we use those features? The answer is yes. We can now start to use those features. So now we're done with problem number one. We found the feature, the points of interest, either the corner, and we solve the problem of the scaling of the corner right now, or the blobs, and we solve the calculation problem of the blobs and the scaling problem of the plots. Next step is what? I need to extract the features around those points of interest. How can I do that? Actually, people spend lots of time thinking about how to do that. The main concept behind this is to find the match. So at this corner point, I need to search the area around it and search the area around this corner point as well to find values that look similar to each other as much as I can. So I have to come up with a way to sample the area around each feature point to find something useful that I can use for the matching process. Okay, no one tell you no. Go ahead. Examine the area around each feature point. What is the challenge? Actually, there are two challenges, not one. Challenge number one. How many feature points we have here? Lots and lots and lots of feature points. So if I try to find features around each one of them, I will spend lots of time. Second, well, the feature vectors around those points will be invariant or equivariant according to the definitions we just started. Like, are they equivariant or invariant against translation, against rotation, against scaling, against illumination? If I can find feature vector that satisfy those needs, voila, congratulations, you're done. You did a great job. Okay. They search about several possibilities to do that. Two very well-known techniques have been introduced and used, by the way, until the moment for some research. One of them called match square window technique, and the other one called SEFT. This one based on the corners. This one based on the blobs. Each one of them have a different way to search for or to find the points of interest, and different technique or way to find the features around it. The most important thing in those feature vector, first, it has to be invariant against the rotation, the translation, the illumination variance, scaling, as much as I can. And it should be unique. Something that I can use to distinguish between this point and another point around it. Okay? So invariant and discriminability. The question is, what exactly I can do to work over that? So it has to be invariant against rotation, against scaling, against this one. Okay? One technique, which is the first technique based on the corner, this said I will do it this way. I will start by the point of interest I found, which is the corner in this case. Then I will find the direction of that corner. How? The direction of the corner will be the direction of X maximum from the H matrix. Remember the Harris operator? We found the H matrix, which include remember this? And we found two eigenvalues, one maximum and one minimum, right? The corner basically determined by the minimum, by the direction determined by the maximum. So I will find the direction of the corner from the maximum eigenvalue associated to the maximum eigenvector, which associated to the maximum eigenvalue. Okay? Some people say, no, I will find the orientation of the smooth gradient. I will take the gradient around this point and find the orientation of the smooth gradient. Both of them will give you the same result, almost. Then I will take 40 by 40 square window around this and normalize it or rotate it to be 0 angle. So this direction rotated this way. So this is the top of the mountain. So this should be 40 by 40. Yes, it's not 40 by 40, it's just an illustrative version, but we are working with 40 by 40 around this point. Okay? Then we will scale it down to 1/5, which is this version. 40 divided by 1/5 equal what? 1/5 of the 40 equal what? 8. So this is 8 pixels. And this is 8 pixels. Then sample 8 squares centered at the features. So those will be my 64 sample. Then I will do normalization by what? By subtracting the mean and divide over the standard deviation. So I will use this technique. I, X and Y minus mu over sigma. Mu is the mean of the window, sigma is the sigma of my window. Why I'm doing that? Why this step is important? Will be against what? First, rotating it to be with a 0 degree to be against this. Putting it down by standard 40 by 40 and scale it down to 1/5 to be against this. Finally, normalization to be against this. Against the intensity. So if I normalize it within the block size, it will be against any intensity change. So if it's dark or light, doesn't matter. Okay, I'm normalizing it against the mean and the variance. After that, this will be my vector. So this vector, 64 by 1, will be my vector of features around this point. Now do this over all the points that you have. Do it also on different scales. And you will have feature vectors that you can use, which is multi-scale, oriented invariant, batch descriptors. Okay? So this technique can work against the intensity, against the rotation, against the translation. Okay? Especially when I work over multi-scale version of it. Any problems so far? Okay. As I said, this technique is built on the Harris corner detection because it finds the orientation mainly from the Harris matrix. On the other hand, some people said no, we don't want to do this. We want to use the blobs. And we want to focus more not on the value of the image. No. We want to focus onto the orientation of the gradient. What does this mean? Listen, around each blob point, I will take 16 by 16 square window. So assume that this is 16 by 16. This is 8 by 8, but consider it 16 by 16. I will calculate the edge orientation. What is the edge orientation? How to calculate it?
Arctangent. Arctangent,
Arctangent what?
the magnitude.
An inverse of the derivative in the y direction over the derivative on the x direction. Remember the Soper filter? We have derivative on the y direction and derivative on the x direction. After finding these two derivatives, if we divide sy over sx and find the tan inverse, we can find the orientation of the edge. Okay? So I don't care about the edge itself, I care about the orientation of the edge. Okay? So here we still need the Soper filter. Okay? Now, I'll calculate the gradient, the theta for that, 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 and so on. Then I will start to quantize them. What is the meaning of quantizing them? I will round them up. Divide. Both are the 360 values, 2 parts. I will divide them into 8 values, starting from 0. For 1, 2, 3, 4, 5, 6, 7, 8, and return back to this. So 8 values, starting from 0 back to the 0. So any value close to each one of them, I will approximate it. Okay. Then I will start to throw out the weak edges. Any weak edge, something that doesn't look like edge, ignore it. Then I will create histogram of the surviving edge orientation. Again, what is the histogram? By definition, when we started the course, what is the histogram? The frequency of occurrence of a specific value. So this value occur how many times? So for those 8 values, I will find the histogram for each one of them. After that, I will divide this into 4 by 4. So the histogram of this one will be here. The histogram of this one will be here. The histogram of this one will be here. Histogram of this one will be here. Now, those 4 by 4 represented now with how many numbers? The 8 value that I have for the orientation. This one represented by 8. This one represented by 8. This one represented by 8. Originally, I started by 16 by 16. Then I divide them to 4 by 4. So 4 by 4 equals 16. So 16 by 16 times 8, it will give you 128 dimension descriptor. Those will be the descriptor of the SIFT. So the SIFT use the blocks detection technique using the difference of Gaussian. And we can apply this on different scales as we described here. Then, at each plot point, I will start to find the 16 by 16 went around the plot point, find the gradient of the edges around that, divide them into 4 by 4, find the histogram of each 4. So this histogram is just 8 numbers. This is 8 numbers, 8 numbers, 8 numbers. I will put a vector with each 8 numbers next to each other for this 16 by 16, sorry, for this 4 by 4, the 16 value, it will end up by having a vector of 128. 128 by 1 dimension vector. Those are the descriptors around the point of interest for the set. And that's what we call scale invariant feature transform set. Okay. Why we are calling it scale invariant? Because we are using the scaled version of the difference of Gaussian to find the plus. Second, feature transform, because we are using the orientation of the edge as a feature in our detection code. Is it clear? Now, if this feature or this technique of the set is good, actually, yes, it's good. It had, when it has been introduced, it was one of the state of the art by that time. It comes to the point that the authors of the paper of set patent. So it became a patent version. So no one could use it by then until they paid the money for the author of the paper. Okay? The SIFT technique, they found that it could handle change in the viewpoint up to 60 degrees out of the plane rotation. Meaning 60 degrees in this direction or this direction out of a plane. It can handle significant change in illumination, which makes sense. Why? Are we measuring any pixel value here? No, we are measuring the orientation of the edge. So if the image is dark or light, the edge will disappear? No, the edge exists. And the orientation of the edge still exists. Okay? So orientation of the edge will be invariant against the illumination. Okay? They claim that it's fast, but unfortunately it's not fast. It's slower than the other feature that came after it. Okay? They claim when they try to use it in real time, they found that it's failed. So for one image, it takes, based on the claim, less than 1 second. But in practical use, it will take more than that. The original code for this set found by the original author of the paper, this is the original paper, if I'm not mistaken. By David Louis from University of British Columbia. And this is the link for the original paper, if you want to check it. He implemented actually as a DLL. He didn't put the implementation available for people to use. And anyone who wants to use it, he has to download the DLL from the website and include it to his project. That's why people did not like to use his features. They try to avoid it. They try to skip it and try to find alternative techniques. We will come through those techniques later. So, the features of the set will try to find information around the edges for the plots. So as you can see, they are mainly trying to find the plots in the given data, then try to find the histogram of the orientation around it. Okay, so here, as you can see, this is 868 SIFT feature. So each square from those has a feature vector value corresponding to it. Okay. People didn't stop here, actually. As I said, people start to find another technique. One of those techniques was the histogram of gradient. Someone said, okay, I like the concept of the set, but this concept of set, try to find descriptor around the points of interest. Okay. Why should I do that? I may try to find the histogram of the gradient for the entire object. So for me, as a human, I can find the histogram of gradient around every place here. It will give me some pattern. I can compare that pattern for the human pedestrian, as an example, with any other human pedestrian, and I can detect this object based on that. And this technique actually very efficient, the histogram of gradient, and still used until the moment in many applications. Okay, so it focused mainly on having a window. This window slide over the given image, and for each value in the window, I calculate the histogram of gradient and try to make a match between the value in this window and a pre-calculated pattern. Another technique found called FRIC, which stands for Fast Retina Key Point. This one, we're trying to, or motivated by the eye, the human eye, how they are working. They claim that it can run in real time, and based on that, they use it in many visual localization and mapping for the autonomous navigation. Another version called LEFT, which stands for Learned Invariant Feature Transform. In this case, they remove the S with L, so it will become learned. So they train a deep neural system on those features extracted to can distinguish and match the feature between the images. So, as a conclusion, we can say that we could now detect the key points. We could find the descriptors using different technique, either using different technique, either by the corner or the blobs. If we are using the corner, we can use the Harris operator or any other type of operator that we covered before. For the blobs, we can use Laplacian of Gaussian or difference of Gaussian. For the descriptor, we can use also different technique. We can use the multi-scale window. We can use the SEFT. Even we can use another application or another feature called SURF. We will cover next week. Or in modern world, we are using deep learning to generate the key points and generate the descriptor and do the match. So the deep learning can conclude and put all of this into one point. Okay. Any questions? Okay, let's take a smaller break. Then when we come back, we'll continue our talk. Okay. Now, from now on, we will start to use the OpenCV library to compare the results and the feature extraction technique from the manual methods and the built-in functions on the OpenCV. First thing, how you can install the OpenCV in your computer. As we stated at the beginning of the semester, it's better to have a separate environment for the course. So for the separate environment for the computer vision, you can go to the Anaconda and a navigator, whatever the environment you created, and open the shell for your for your selected environment. Then, once you open, take a moment. So assume that you are working with the OpenCV environment, so CV Python. So you can easily go here and Conda, activate CV Python. So this way, I'm activating my OpenCV, my computer vision environment that I designed or make it just for the computer vision assignments. Then I will start to install the OpenCV packages. How I can do that? Using pip install OpenCV-Python. Watch out for two things. First, which version of Python you have on your machine, because not all Python versions compatible with all OpenCV versions. Okay, if you have your computers have an older version of Python, so mostly for me, I use Python 3.7, and sometimes I use 3.4, depending on the environment. The version I have here right now is 3.10. It will be able to grab the latest version, which I think 4 point something. But if you go to this If you go to this repository of the OpenCV Python, you'll find that the current version is 4.11 right now. If you try to search for Ceph, you will get this message. What is this message saying? Non-free algorithms such as Surf are not included in these packages. So the package of the OpenCV Python by default does not include the Surf, okay? Because they are patent and non-free, therefore cannot be distributed as a built library. Recently, starting from a version 4.3, the Ceph has been included. So the patent has been expired and people allowed to use the Ceph for free right now. But other algorithms like the Surf still unavailable. You can't find them in this version. If you want to find them, you can go to any versions below 3.4. Okay? That's why we need to install something called OpenCV Contribute Python version 3.4.2. Okay? If this gives you error, find any version below 3.4.10 and install it. Any version below this to have the Ceph and the Surf. Okay? This is the best way to reduce the headache. Is there another technique? Yes, there is another technique. If you want to have OpenCV 4.11 with the Ceph and Surf, you can. But you have to build it from scratch. You have to build it yourself. And in the CMake, you have to enable the non-free algorithm and compile it based on that. Okay? So those are the only two solutions that you can use to include the Surf algorithms in your installation. Okay? Why we are talking about the Surf? Because we will need it, because we'll discuss it soon. Okay? And the instructions also will be included in the upcoming assignment. Okay. Now we want to see how those features will look like when we use them. Okay. First, how to use the OpenCV. Using OpenCV is more straightforward than the PIL. So all what you need to do is just import CV2. This will import all the functionality of OpenCV into your code. Then, if you want to read an image, simply you can use cv2.imread, including the path of your image you want to read. Then it gives you the option. If you want to read it as the default format, if it's grayscale, it will be grayscale. If it's color, it will be color, or enforce it to be color. If you want to enforce it to be color, or what you need to do is just add 0 here. So this imread_grayscale is nothing but 0, just numbers. Okay, so this will enforce the image to be read as grayscale. Then you can make resizing if you would like. This not a mandatory part. Then we can use or create a set detect using CV dot X features 2D underscore set dot create. So here I'm creating set detector that will be used to detect the feature and find the descriptor. Here I put the sigma value that I will use. Remember, I start with sigma, then I will go with sigma squared, then sigma cube, sigma 4, and so on. So this is the sigma value that I will start with it. After that, I want to apply this detector over my image. So I will make detector dot detect, and this is my image, the source image I have. The detector has two functions, two main functions. The first one is detect. The second one is detect and calculate. Yeah, detect and compute. Okay, so there is a detect only and detect and compute. What's the difference between them? The detect only will return the points of interest only. It doesn't return the features. So the output from the detect process, the coordination of the key points and the radius, because this is a block, right? So the center of the block and the radius of this block. If you use detect and compute, it will return two things: key points and the vector around each key point. The vector of 128 by 1, which is the histogram of the gradient around each point. Now, if I want to visualize this, can I see it? The answer is yes. All what you need to do is create an empty image with the same size as the original image, then draw those scope key points inside or on those image and return it to this empty matrix. That's it. So if I run this code, that's how it will look like. So those are the basic blobs at sigma 26. Then it had the other variations of it. Sigma squared, sigma power 3, sigma power 4, 5, and so on. Okay, so this is the minimum sigma value. Okay. Any questions? Now, assume that we are successfully found the points of interest. We found the descriptors around the point. What should be the next step? The final and the next step should be the matching. I will try to match the features I found from those image or around these points to the features around to the same points and so on. How can I do it? Based on what we saw so far, we have lots and lots of key point features here. And we have vector around each one of them. And the other picture will have the same thing. So how I can match them? How I can find the point here and the corresponding point to the other side. This is exactly what we will do in the feature match. So the feature match technique means I have features on this one, and I have features with this one. I'm trying to see which one here match which here. So this is the feature matching problem. Okay. What is the information I have so far? What exactly I know in my hand? I know two things. This coordination, and of course the radius of it, and the vector around it. Okay, so those are the information I have at each point. My job right now is to list all of those as a vector, list all of those as a vector and match. This is 1, 2, 3, 4, 100 as an example. And those again, 1, 2, 3, and 100. So which one match which one here? It's exactly like connecting. You know, when you were in elementary school and give you the names of the apple, banana. Let me arrange them. So you are connecting them like this. That's exactly what you want to do. Which feature here corresponding the which feature here? Okay, how can we do that? So to do this process, we need to define something called distance. What is the distance? In general, if you have 2 points in the space, and I ask you to find the distance between them, what you will do? Seriously? So I will need to find this, the length of this line, which can be defined using the equation of right? This is actually, we call it Euclidean distance. Okay, so the Euclidean distance is the distance between any 2 points in the Euclidean space, which consider the space as flat. Okay, what if we have 3D? The question would be what? But the equation of the distance in 3D. What if I have 4D? Same thing. 5D, same thing. So I can generalize this to be square root of summation of xi minus xj over all the x and j squared. This is a generalized Euclidean distance. It can have the symbol L2 or called Euclidean distance. So it has different names. Is it the only distance we can use to find how far the points from each other? The answer is no. There are some other metric distance that we can use as well. As an example, there is another one called L1 or Manhattan distance. So if I want to find the distance between those 2 points according to the Manhattan rule, I will find absolute value of x1 minus x2 plus y1 minus y2. No square, no square root, just modulus. So this is similar to blocks. If you are in downtown Manhattan and you want to go to some place, what will happen? It will tell you go 2 blocks this way, then 3 blocks this way, right? That's exactly what we are doing. Number of blocks in the x direction, number of blocks on the y direction. That's it. Okay, that's why this one called Manhattan distance. If this is the only 2 distances, the answer is no. We have many definitions of distance. Some of them assume the points are in the Euclidean space, the surface is flat. Some of them on the non-Euclidean, like finding the distance on a pole. If you have 2 points on a pole, can you find the distance between them? Can you find the distance between 2 points on a pole? Can you? Well, this rule valid? Will this one valid? Will this one valid? Is this valid? No, none of them will valid. Okay? There's a completely different rule. You have to project this into an Euclidean space first, then use those rules. You can't apply those rules directly to a non-Euclidean space, okay? Which is a different type of geometry, okay? But again, we are using this type of geometry also in the vision. Okay, so in this matching process, we will assume that we have 2 descriptors. And we want to find the distance between those 2 descriptors. Mean, I have number 1 from here and number 1 from here. And I want to measure the distance between those 2. Is it short or no? If the distance is short, then they're similar to each other. If the distance is large, this means that they are far from each other. Okay? So I will measure the distance between this one and 1, 1 and 2, 1 and 3, 1 and 4, 1 and 5. So I'll come up with a pairs like this. the distance between each pair. Then I will find the minimum against them. The one with the minimum distance is the match. Okay? Then I will do the same thing with the second. Second against all of those. Third against all of those. Fourth against all of those. And so on. Now, if we assume that I have, as I stated, 100 key point feature here, 100 key point feature here, and I want to do this match, how many distance I have to calculate?
Like 100,000? Or
100,000?
10,000?
10,000?
What's the range?
What is it?
What's the range we're talking? Is it like millions?
Okay. Do you understand the concept? The concept is we are measuring one against all.
Yeah.
Then go with the second against
Oh,
all.
yeah, which is 100 each one, right?
Right.
Right.
So it's exactly as if we're filling a matrix. So if this one has M and this one has N, we are calculating M times N, which is the 10,000. Okay, you were correct. Okay, so I have to find this minimum distance by calculating all the match between the features from this side against the features from the other side. Then I will find the minimum distance, and this one will be the best match between them. Okay? So, assume we will use the L2 distance. We can give it this simple. Again, L2 distance means Euclidean distance. Like square root, this minus this square, this minus this square, and so on. Okay? So, if I have a vector that has 128.1, this is x1 and x2. 128.1, I have to do this minus this square, plus this minus this square, and so on, then take square root of all of them. It doesn't matter what the dimension. I don't care. Okay? Then find the shortest distance or the one with the smallest distance between them. But what if I had this case? In this case, the point of interest here, feature vector around it here, and another one is here, another one is here, another one is here. Same here. Now, if we found a match between this and this is the minimum distance that we found. Is it really minimum? Is it the correct one? The correct one is what? This one. But this one shows the minimum because it's similar to this from the reconstruction. What should I do? In this case, the minimum concept didn't work well for me. I need to tweak it a little bit. Based on that, we said, I will calculate the smallest error between the first match and the second match. So this is the distance between F1 and F2. I'll take the distance between F1 and F2 dash. So instead of working by pairs, this against this, no. I will find the ratio between this and the next close one. And I will do this against all the matches. Based on that, I will have a ratio distance, error distance, that can be used to work my match. So, as you can see, I can have this input, and I found the features from the points here and the feature around them. Then again, the features here and the features around them. Then I can try to make a match between them, and I can find this ratio distance or ratio score between them. So this ratio score is nothing but a ratio between the distance between F1 and the highest score and the second highest one. So it becomes ratio rather than just a number. Okay? So if there is a high match between this and this and this and this means the ratio will be 1. So it's almost the same. I have many of them. But if the ratio between this is high and the ratio and the distance between this is high, sorry, and this is small, this ratio will be high value, not 1. So if this ratio equal to 1 means the match is weak. If this ratio is big, then the match is strong match. Is it clear? So I'm not relying on the number itself, the distance. No, it's the ratio between the first match and the second. How I can find the first match and second match? By sorting this. Remember, calculating 1 against 1, 1 against 2, 1 against 3, right? Then I will sort. Then I will find the minimum and the second one after the minimum. So this is the first match and the second match. Using this ratio will give me better understanding of the ambiguity in my data. So will it always work good? The answer is not really. Sometimes we can find matches far away from the correct one. We are calling this one outlier. I heard this word before. Where did I hear this word? We came up through the word outlier just before the break. The ransack. We said that the ransack algorithm is not basically, or it's not designed for line detection. No, it's designed to remove outliers. That's how originally it's designed for. Okay, so I can use the ransack to remove the outlier in this matching process. Okay, so while you are doing the matching, I can do random sampling and match at the same time. I will not match all of them with all of them here. What are the benefits of that? Instead of calculating this one, I will reduce it because I'm random sampling right now. Couple of features from here, couple of features from here, try to match them against each other and find the ratio. So I reduce this less into maybe half or maybe less. Okay. So having or using the ransack algorithm can help us reduce or remove the outliers and make a robust matching technique. Now the question is, I did the process and found the match. How I can judge if the match is good or the match is bad? I need to quantify this, make numbers that can give me the quality of the match. Can you do that? The answer is yes. So assume that we have 3 features here and 3 features here. The distance between this and this come with the minimum distance of 50. This and this minimum distance of 75. this and this come with a minimum distance of 200. Is this a good thing? So this is good. And this is good. Is this a correct match? The answer is no. This is an outlier. And I need to remove it one way or another. To understand and to remove this or to judge this matching process, I need to define some terminologies. The first one, I will call it true positive. What is the meaning of true positive? It means the number of detected matches that survive the threshold that are correct match. So those matches with each other and they are correctly matched. So this is considered to be true positive, number one. This one correctly matched, and this is number two. So I have two true positive. Another thing I will call it false positive. What does this mean? Match that survive from the threshold or the minimum distance, but they are not correctly matched. Like this one. So in this one, I have two true positive, one false positive. Okay? Now, what should I do with these numbers? Our goal right now is to maximize the true positive as much as I can. What is the threshold value that I will choose for this ratio distance to achieve this maximum threshold? Remember, I'm now calculating this ratio distance, then I will threshold it to find the minimum limit. The one above it is matched with it. Now, what is the threshold value that I should choose that can give me good or maximum false positive, true positive value? This threshold actually will be a trick in my calculation. How? Let's see this example. Assume that we have two images. Each one of them has 1,000 features. And we want to find the match between those 1,000 points. 8 of them are correct after the match. 200 are incorrect. Now, in this case, the ratio of the true positive will be 3/4. The ratio of the true false positive will be 1/2 or 1/2. I will put those numbers into a chart. The X of the chart is the false positive. The Y of the chart is the true positive. So at this half, the value is 34. Then I will change the threshold of the detection. For this ratio, I'll change the threshold for the detection and find the new value. Change the threshold, another value, change the threshold, third value, change the threshold, fourth value, and keep going like this. After that, I will connect those points together, and this will give me something called ROC curve. ROC stands for receiver operator characteristic. So mainly, this curve has been designed to measure the quality of the received signal over RF. So after thresholding we convert it into digital, and we check the correct over the false rate. Here we have similar stuff. We have matching, and we are changing the threshold to find the amount of good match and the amount of a bad match. Okay? The false positive rate here, we call it specificity. It's hard to pronounce. Specificity. This true positive rate, we call it recall. And this curve, which is a function between the false positive rate and the true positive rate, called the ROC curve. Now, how the ROC curve can judge my matching technique, if it's a good or bad? Simply, I can measure the area under the curve for the ROC, and this area can give me indication if I have a good match or a bad match. If the area under the curve bigger than 50, then you have good match. If the area equal 1, you have a perfect match. All the points here match the required points here exactly correct. And in this case, the curve will look like this. Going exactly to the corner. So the area under it will be 1. Because it's a square, right? 1 times 1. So the area will be 1. If the area is 1, then you have a perfect match. Your matching technique undebatable. If the area less than 50%, of course I'm talking about 50% or 0.5. This is a bad matching technique. In this case, the curve will look like this. Under this middle line. This means that this technique is horrible. This middle line actually, or this 50%, is the chance. If you toss a coin and see if this is good or bad. So this is the 100% chance, tossing the coin probability. Lower than this means bad, upper than this is good. Okay, so looking to the ROC curve can give you indication about your matching technique. Okay, again, how we generate the ROC curve? How we generating the ROC curve? Start by the matching points. I will measure the ratio. Then I will use threshold. Let's say my threshold here was 250. So all values above 250 considered to be matching. Based on that, this point matches this point. This point matches this point. This point matches this point. For this threshold value, I will go and measure the true positive versus the false positive. Then I will find the ratio of them, the rate of them. Here as an example, I have the total number of points is 3. 2 of them match. So I have 2/3 true positive rate. Here, the false positive will be 1/3 false positive rate. So I will go to the curve and add this for this threshold limit. Change the threshold, do the same thing again. Change the threshold, do the same thing again. Keep doing this again and again and again until all the data become wrong. If you have 100% false positive means what? All the data is wrong. If you have 100% true positive means all the data is true. So I will keep doing this until I include all the data to be one, then plot the curve. After that, I can determine the quality of my algorithm based on the selected value. Is it clear? Okay. So if I want to plot the ROC curve, first I have to find different threshold values for the ratio distance. Then I'll calculate the false positive rates and the true positive rates at this threshold value. And this value will be converted into 1 point into the ROC curve. Then change the threshold again, calculate the rate again, change again, calculate again, change again, calculate again, until you arrive to, or you fill the whole entire curve. Okay? So the ROC curve will be generated for a set of threshold values, not for one, multiple. Okay? I'll change for them, then calculate all the false positive rate and true positive rate. The area under the ROC curve, as we stated, can tell us the quality of my features and the feature matching technique. Okay? So just by looking to the ROC curve, I can say that this is the feature view are good features and the matching technique is a good matching technique or vice versa. Okay? Now, I can use this in many applications. Now, we found the curve of the states right now. We now learn how we can find the points of interest, we can find the descriptors, and we learn how we can do matching. Now, we fill all this requirement, I can do anything I would like to do. Like what? Like image alignment. If I have multiple images and I want to align them together. If I want to make 3D reconstruction, I have a couple of images and I want to build 3D view for an object. Motion tracking. I think I showed you before the the SLAM algorithm and how it works with the visual odometry. I can do object detection and recognition by finding the object in the environment, like here. I'm looking for this object inside this image. So I can easily find the features of the object by itself and find all the features inside the image, then try to make matching between this and this, and try to find the boundaries based on that. Same for all the objects I have here in the image. Even though the object may be 100% viewed, as you can see, the shoes here is partially covered by the bear. And the phone is partially covered also by the bear. But I still can find the match between them, even with this partial occlusion. But again, this still, or this has lots of limitations. I'm not sure if I show you this image before, but let me show you this one. I think I showed to you in lecture 1, did I? Yes, this one. Can you find the cat here? Can this SIF technique find the cat? So the other example that we show have partial occlusion. This is also has a partial occlusion, but the only tail and part of the hand is shown. Can we find the cat using the SIF as an example? No way, don't try. It will not work well. Okay. On the other hand, with the deep learning, it can find. So the deep learning can work with those tough and challenging examples like this, or even those in much better way. So those consider to be a very challenging examples. Okay. Using SEF or SERV or any of the features we are covering so far is not the perfect way to handle the job. Can it handle it? Yes, but not the perfect way. Okay, we need to pre-process the images one way or another before using those feature matching technique. But they still have many algorithms or many applications rather than only the search. Like the reconstruction, we still use the same concept of feature match until the moment for the 3D construction. So if I give you 2 or more than 2 images, I can reconstruct 2.5 or 3D view for some scene using the technique we covered so far. Only by finding the feature and match them together, I can combine this data and build this 3D view. And of course, we are using it in many of the augmented reality applications that we have in the market so far. Okay, any questions? Okay, I think you have enough of those for today. But maybe I will add some extra video on Canvas for you to watch on your convenience. Okay. Any questions? Any problems?